Okay, so this is the rough outline of the talk. There's several parts, and it's sort of an intersection of two areas. So I want to tell you about both areas to get a sense of what's going on. So the main area is proof complexity. Then I want to tell you about specifically what is an algebraic proof. I need to then motivate this algebraic complexity, which is another area of study. And then this ideal proof system is a particular algebraic proof system that incorporates ideas from algebraic complexity. And then I would tell you what we did in this work. There are sort of lower bounds for this ideal proof system IPS, and then some upper bounds if I have time. OK, so what is really this area of proof complexity? It's sort of like circuit complexity, but it's really trying to understand the power of sort of non-deterministic circuits in some sense. So let me just give you an example. Suppose you have a statement something like the graph G, say on n vertices, is 3-colorable. So this is a finite statement about a particular graph G, which I have in mind or something, and it's either true or false, right? And if it's true, right, then we all know that there's a linear size proof, right? You just sort of give me the 3 coloring, and I can verify that this is a valid 3 coloring. But suppose that it's false, right? How do you prove that this statement is false in an efficient manner? And I'm going to sort of you could talk about proving the negation, but I want to use a different language. I want to say I want to refute phi. That's like the terminology proof complexity. So I want to refute phi, which is proving the negation. And there's no sort of known polynomial size proof, polynomial in n in general for a general graph G. And this is sort of what you would expect, because if there was one, in general, this would imply, say, NP is equal to coNP, which we don't really expect to be true, right? So if you assume that NP is different from coNP, then you don't expect such proofs. And so roughly speaking, the goal here is we want something like a super-polynomial lower bound for the size of proofs. And I mean, ideally, we want something unconditional. Obviously, as stated, this would prove NP different from coNP, so we don't expect to do that. And so it'll really be sort of restricted proofs. So proofs in some natural restricted way, and we want to get unconditional lower bounds there. And what are some examples of proof systems? One well-known proof system is the Frege proof system, which I'm not going to define. But it's basically, if you go into any logic textbook, they'll give you some sort of proof system for proving statements about variables and boolean variables, and that's the Frege proof system, basically. There's something called resolution, which usually deals with boolean formulas in conjunctive normal form. There's cutting planes, which is related to integer programming. And then there's also like the sum of squares proof system, which is related to semi-definite programming and so on. Okay, so there's a number of proof systems, and basically what people in proof complexity do is they study one of these systems. They look at statements like the following, or encoded inappropriately, and they say we want to prove super-polynomial low bounds for the proofs, or in terms of how easy it is to refute these statements. Okay. But what I want to talk about is algebraic proofs, and so what are those? So it's a different way of encoding statements like this. So let me just do a really stupid example. Suppose phi is the following Boolean formula. You have x. Am I getting this right? Right. So you have Boolean variables. In this case, you'll have 2, and this is some conjunctive normal form Boolean formula. And you want to know whether it's true or not, or satisfiable. Is there a setting that makes it true? In this case, it's not satisfiable. And the point is that I want to encode this into algebra. And how can I do that? Well, this is satisfiable if and only if the following system of algebraic equations is satisfiable. So first, I want to encode that these are Boolean statements, Boolean formulas. So I can consider equations of the form like this. X squared minus x is 1. X squared minus x is 0. Which is satisfiable if and only if x is 0 or 1, right? And then I can also throw in equations like 1 minus x, which is saying that x is 1. Then you have x 1 minus y, and y equals 0. OK. So this is, a way of encoding a Boolean formula into a system of polynomial equations, which preserves satisfiability. And so basically now you can say, given a system of polynomial equations, how can you prove that it's unsatisfiable? And that's the algebraic proof system sort of stuff. But the point here is that the polynomials that you get out of this reduction, they're not arbitrary. So they're sort of an ideal or perspective or aesthetic or something, which is that you want polynomial equations that are local or simple. Right, typically, if you want to talk about satisfied Boolean formulas, you talk about conjunctive normal form, you talk about 3 CNFs. And if you did this in coding, you would get polynomial equations which are always on, say, 3 variables. So we're not necessarily going to be talking about proving unsatisfiability of arbitrary polynomial equations, but polynomial equations arising maybe from this reduction or in ways that the polynomials themselves are simple or local. We won't always get this, but that's sort of the goal in mind. That they only operate on a small number of variables. Yeah. OK, so that's the ideal, but anyways. OK, so how do we actually do a refutation? Well, there's this like Hilbert Nullstellensatz, which is which is a way to give a refutation. So we're going to have polynomials f1 up to fm, and they're going to lie in some ring of polynomials. And just for notational purposes, let me call the variables here will just be x bar, vector variables, and the polynomials will be sort of a vector polynomials f bar. OK. And what the Nullstellensatz says is that f1 of x, this has a common solution when you set all these to 0. This has a common solution in the algebraic closure if what? If only if, or it does not have no solution. If and only if there's a certificate, a proof that there's no solution. And the proof of this is a particular, there's g1 up to gm polynomials that you have such that it obeys some equation, which is that g1 times f1 plus gm times fm is 1. OK, so the point is that to certify that there's no solution, you just give these polynomials here and verify that this equation holds. OK, and it's pretty easy to see that if you can exhibit these things, then there must be no solution, because if there was a solution, you plug in that like particular variable, that solution here, and this would each of these f's would become 0, and then you get 0 as 1, which is a contradiction, right? So the other direction is obviously much more complicated. But the interesting question here is what can we say about efficiency of this proof system? Right? If we say applied this proof system to this system of equations, like can we say that there is an efficient proof or not? Now, as written, the theorem doesn't tell you anything about how complicated these g's must be, and in general, it's actually exponentially complicated. But the point is that the polynomial equations we're studying, they're not going to be arbitrary. We're always going to have these Boolean axioms. We'll only be interested on systems where all of the possible solutions are 0 or 1. Right? In that case, we can actually do a little bit better. OK, so the lemma here is suppose that you have a system of equations which I'll write this way. OK, so f here is going to be, again, some vector of polynomials. This notation here, I'm just going to write for the set of equations xi squared minus xi. Okay, so this is some system of equations. We want to know whether it's satisfiable. And this is unsatisfiable if and only if there exists a g and an h such that, well, the same sort of equation holds, right? such that the summation of Gj, Fj plus Hi, right, so it's the same thing where I'm using G's to represent the coefficients of the F's and H's to represent the coefficients of these Boolean axioms. But now, because I have these Boolean axioms here, I can actually bound the complexity of these. So the Gj's are necessarily multilinear, so that if you look at each variable xi in this polynomial Gj, then it doesn't appear with a quadratic term. It just has individual degree at most 1. So in particular, the degree here is at most n. And the degree of the hi's is at most order n. And so if you actually take these two conditions, then that says that the complexity, or the descriptive complexity of G and H is at most exponential in n and m, say. OK, so that's saying that when you're looking at polynomial systems equations over Boolean variables, there's a proof of at most exponential complexity, which is sort of what you would want, because intuitively you could just enumerate over all possible Boolean values here, and there's only exponentially many of them. So there is some proof of exponential complexity. And the question is, when can you do better than this sort of trivial bound, right? OK. Right. OK. So we wanted to say when can you do better, and how can you measure the notion of better? And so there's two notions. OK, so in terms of efficiency.
In this special case, is easier than the general?
Sorry?
Is it like an exercise to prove the special case?
Yeah, so this is an exercise. Basically, the way you do it is you do induction on variables. So you say, suppose that you have a system like this. If it's unsatisfiable, then it's certainly unsatisfiable when you set x1 to 1. And it's certainly unsatisfiable when you set x1 to 0. So by induction, there should be a proof when x1 is 1 and proof when x1 is 0. And then you just combine them in sort of an obvious way. And then you get a proof for when x1 is unrestricted, right? And then you have to do some division outcome stuff. But it's more of an exercise. General cases, not so much. But OK. OK, so how can you measure efficiency in the system? Well, one is with degree. So here I said that the degree is at most n. But suppose it was much smaller. Like, what does that tell us about the complexity of this proof? Well, then so if the degree is at most d, then the size, the descriptive complexity of these is something like polynomial in n and m to the d. So if d is particularly small, then you get a small proof, so like constant or something. Another measure of complexity is when G and H are, say, S sparse. So what does that mean? That G and H are sort of tuples of polynomials. And suppose that each polynomial is a sum of, at most, S monomials. That is some notion of simplicity. In this case, the size of the proof is, say, polynomial in n, m, and s, in some natural situations at least. OK. And so if either of these parameters are small, then you get a small proof. But in fact, previous and so you can ask, can we come up with explicit systems of polynomial equations where any proof must be non-sparse and high degree? OK. And there has been some, indeed, previous work has shown, explicit systems of equations where the degree must be n to the omega 1, and the sparsity is at least some exponential factor. So in both of these are basically at least polynomially close to what you would expect in terms of the maximal degree, maximal settings. So there are explicit systems, even coming from encodings of 3C and Fs and so on, where any algebraic proof of this form is basically of maximal complexity, up to some factor. Okay. So it seems like maybe we're done, but I'm still giving a talk, so we're not done. And basically, Grochow and Pitassi, in a paper in 2014, they asked this very nice question, which is that degree and sparsity are very coarse measures of simplicity of a polynomial. Can we more succinctly represent proofs? So can we succinctly, or more succinctly, represent G and H? Like it could be that there's much more structure to G and H, and we can use that to compress them somehow. And in these more succinct ways, can we still get lower bounds? Okay. And so to tell you about these more succinct representations, I need to tell you about algebraic complexity. Okay, so algebraic circuits. So let me give you just an example. Which is my favorite example. So consider the polynomial x squared minus y squared. So it is a sparse polynomial. There's only 2 monomials here. But I can sort of compute it in another way. So for example, I can compute it as in its factorization. X minus y, x plus y. And you can write this as the so-called algebraic circuit, which is, in this case, a tree. So you have x. So I did this factorization, and then I'm going to say this is equivalent to this diagram. Right? So you have a multiplication gate, which is multiplying these 2 factors. Here you have x plus y, and you have x plus y times minus 1, which is minus y. Right? So x minus y. Okay. And I want to say that this is a general sort of model of computation. So what's sort of the definition? Sort of an algebraic circuit, right, is a directed acyclic graph. And there's going to be there's one output gate or output node, which is the sort of unique node with fan out 0. There's going to be internal nodes. These are going to be labeled with multiplication and addition. And then leaves are going to be, they have scalars from the fields, and your variable is xi. Okay. And this will compute in a natural way where you basically have internal nodes. They'll either add or multiply their children, and so on. Okay. And the usual restriction is we say it's a formula if the fan out is always 1. In this case, here it'll be a formula, for example. Okay, and the important notion here is what is the size of such a computation? This is the number of nodes. Okay, so we'll say that a polynomial can be computed with a small algebraic circuit if there's a small algebraic circuit where the size is small, right? And that's the question that Grochow and Pitassi were asking: is can these proofs be represented as algebraic circuits where the size is small? Because sort of sparsity and degree are sort of coarse measures of these size. I can do one more example. Okay. So maybe a motivating example of this question is you can consider sort of a silly polynomial like this. You have x1 plus y1, xn plus yn. This has a linear size circuit, right? But the degree here is n, and the sparsity is 2 to the n. So if you sort of go to how these things translate, the fact that the degree is large means that if you sort of translate that to the size bound, that's a really terrible exponential bound. The sparsity is also exponential, but you can represent this polynomial as a very small circuit. Right?
Polynomials in the previous works has low degree.
Sorry?
Low size.
Which,
The previous works.
So yeah, typically the explicit systems come from things like CNFs. So you're going to have systems like this where all of the axioms in your system are going to be local, and they're also going to be constant degree axioms. But then the proofs or the refutations of those axioms may be required to be large degree. Does that make sense?
Yeah, I was trying to ask whether the G and the H's in the previous works had low sizes.
So no one's proven that. Like, so, I mean, so, you know, previous work, they've studied the degree, they've studied the sparsity, but no one's shown that for interesting models of algebraic computation, they require large size. And so that's basically what we're doing now. Okay. Okay.
But the same construction.
No, it'll be different constructions. Yeah. Well, yeah, there'll be different constructions. Okay. So let me. So one of the challenges in this work is that there are lots of different models of algebraic computation.
But maybe like related to what Pilar was asking.
Yeah.
So you could maybe prove lower bounds on degree and sparsity for things that are easy. I mean, can you do a separation between the two?
Yeah, you can. So I will tell you a separation. Yeah. Okay. So, right. Okay, so the challenge here is that in general, we cannot prove lower bounds for general circuits. And so we need some even restricted model of circuits that if we want to prove lower bounds. And I will give you some upper bounds that will give you a separation. So I want to just give you a small, very simple model of algebraic computation, which can be much more succinct than sparsity or degree, but is still weak enough that we can prove lower bounds. And so this model of computation will be a small depth formula of a particular kind. So you'll have a summation of j1 to r, and then you do a product over the variables. And here you have aij xi plus, let's call this beta, beta ij. Okay, so this polynomial is linear, and it's also a univariate. A univariate polynomial, it only depends on the variable xi. And there you have so you have a product of univariates, and then you take a sum. And so I'm going to call this, there's not really a good name for this class. I'm just going to call this the baby case. Okay. And this baby case cannot actually compute that polynomial that I gave you over there. You can prove that. But it can compute polynomials that are non-sparse. For example, you can consider x1 plus 1 up to xn plus 1. Right? This is a very non-sparse polynomial, and it's high degree, but it has a very simple expression of this form. Okay. Okay, so this is the lower. I'm going to give you some lower bounds for. Also, this model can compute any sparse polynomial. It's also so that it subsumes the sparse polynomials. And what I want to do in this work is to give you lower bounds for explicit systems of equations that any refutation requires large size in this model. That's what I particularly want to argue, amongst other things. Okay, so now I need to tell you just more about this ideal proof system and how it sort of unifies this perspective of measuring proofs succinctly as algebraic circuits. All right, so we have this ideal proof system, which was introduced by Grochow and Pitassi, which is basically taking this Nullstellensatz and asking that each of the proofs, the G's, are of small size. Right, so we'll say that this system F, when you add in the Boolean constraints, has a size S, and this is called IPS. IPS refutation. If there exists G and H, basically as before, where summation Gj Fj plus summation Hi times this, it obeys this Nullstellensatz functional equation, and each Gj and Hi have size S circuits. But of course, you can then restrict IPS to any situation where you restrict circuits not to arbitrary circuits, but to circuits, say, from the baby case. Okay. And what's interesting about this system is that when I talked about degree and sparsity, I gave the sizes of the proofs. And the one thing that people really want from proof systems is that you can check them. Like, I'm giving you a proof, and you want to verify that the proof is correct. And when I defined size, I really had in mind that this is basically the size of the proof, and I can verify the proof polynomial in this size. Okay. With the IPS system, it's easy in the sense that we don't actually know how to verify IPS proofs deterministically, but you can do it in randomized polynomial time. Right, so the dilemma here is that IPS refutations, they can be verified in randomized polynomial time, which, for most practical purposes is fine, as practical as you can get in complexity theory. But the point is that why is it randomized? It's basically, if I give you these f's will typically be of constant size because they'll be maybe constant degree on constant number of variables. And if the gj's and hi's have small circuits, then this is some polynomial expression. And you want to verify this polynomial expression is equal to 1 identically as a polynomial. And this is an instance of this problem of polynomial identity testing, which has randomized algorithms. Basically, you just evaluate this expression as a polynomial at a random point and check that it's equal to 1 in this case. But verifying the expressions like this deterministically is an important challenge in de-randomization that seems challenging, and so we don't actually have better algorithms in general. Okay. Okay. So this is saying that modulo the fact that you can only verify in polynomial time, this is a legitimate proof system. And an interesting question is just how powerful is this proof system, like in relation to other well-known things. And so Grochow and Pitassi, they studied this question and related this system to other systems like the Frege system I mentioned earlier. Clearly, it's much more powerful than just measuring in terms of sparsity and degree, at least intuitively. But let's see what they actually proved. So I didn't define the Frege proof system for you, and I'm not going to. But it's basically a very natural proof system that's roughly on the level of NC1 formulas. So it's sort of in terms of Boolean circuits. So it's a fairly powerful proof system that captures most proofs that at least I can do. So what they proved is that the ideal proof system it can simulate efficiently Frege proof systems. And so what does this mean? It says that if you have something like this is sort of you have to parse this statement because IPS is about algebraic systems of equations. The Frege proofs are about propositional proofs like on Boolean formulas. So what this is saying is that if you can refute a Boolean formula using a small Frege proof, and you encode that Boolean formula, like if it was a CNF to say, as a system of polynomial equations, then IPS can also refute it with a similar size. Okay. So it's saying that proving lower bounds on IPS would at least for CNFs or encodings of CNFs would imply lower bounds for Frege proofs, which would be pretty impressive because we'd have no super-polynomial lower bounds for the size of Frege proofs. Okay. Also, what's interesting is that there's a follow-up work by Li, Tzameret, and Wang in 15. And what they were showing is that, so Grochow and Pitassi showed some sort of converse, a weak converse, but there was a big obstacle in the sense that, Frege proofs, you can check them in polynomial time, whether they're true or not, a true correct proof. But with IPS, all we know is a randomized algorithm for verification. And so you can't really have an equivalence because we don't know how to do this verification in deterministic polynomial time. what they were able to show is that such an equivalence, and they would say that Frege proofs are equivalent in power to something called maybe a non-commutative IPS proof. So I'm not so much going to define this, but basically the ideal proof system is about polynomials, and this is all about commutative polynomials. But you could equally, consider this in the land of non-commutative polynomials, and say, can you find, certificates of this form where the polynomials and circuits are non-commutative? And that is some well-defined notion. And they're able to show that in this case, you do have an equivalence, because you can actually check identities of non-commutative formulas in polynomial time, due to Ron and Amir. OK, so there is an equivalence there, which is nice. OK, and so the main question left open by these works is, can we get some sort of IPS lower bounds, even for restricted models of computation, algebraic computation, like this baby case? OK, so now I can tell you about this work. And so basically, we're trying to meet this challenge in some non-trivial way. And I want to tell you about the systems of polynomial equations that we're working with. OK, so we'll call this subset sum problem. This sort of well-known NP-complete problem. You're given beta, and you're given n numbers alpha 1 to alpha m. Typically, you think of them as integers encoded in binary. And the question is there a subset that sums appropriately? So is there a subset S such that the summation of these alpha i's is equal to beta when you restrict the alpha i's to be in the set, right? So this is NP complete in NP complete in general. And so you can ask, can you refute, if there is no such sum, can you prove it efficiently? Okay. And as stated, this is not a CNF or a Boolean formula, but it has a very natural encoding as a polynomial system of equations. And what is that encoding? Well, basically, you consider the linear polynomial alpha I xi minus beta along with the Boolean axioms. Okay. Right. So clearly, this restricts to Boolean solutions, and then basically the setting of the xi's pulls out the subset, right? And this is satisfiable if and only if there is such a subset that gives you the sum. Okay. So the question is, consider this axiom system. Can we get short IPS proofs for this in any way? Okay. And so there's this previous work on this axiom system due to Impalagazzo, Pudlak, and Segal from '99, ironically acronymed IPS. And they foresaw the future. And they studied this system. And the interesting thing about proof complexity is that typically, when you want to prove lower bounds, you need to understand, you cannot refute a true statement, right? That's sort of trivial, right? So, if you consider true statements, you can get a lower bound of infinity on the proof size because there's simply no proof. So that's not really that interesting. And so really, you want to refute statements which are false to get interesting, lower bounds. And to get proofs of things that are, or refutations of things that are false, to some extent, you need to understand why they're false. And so this sort of says that you can't really understand, arbitrary systems very well because you don't really understand why arbitrary systems are false. At least that's my perspective. So what you want to do is you want to consider a very simple case of the system where it's false. And what's a very simple case? We'll consider this system. Okay. So here, all the alpha i's are 1, and beta is -1. Okay. So this is sort of trivially unsatisfiable because we'll work over like characteristic 0 here. This will always be positive, right? Strictly positive, and so it's never going to be 0. Okay. And so what they were able to show is that any well, it's not really, they didn't really use the, this term of IPS since it's for the definition, but they looked at, Nullstellensatz proofs, which in this case is the same thing, and they said that basically any IPS proof is of degree omega n and sparsity exponential n. Okay, so this is saying that if you just look at these coarse measures like degree and sparsity, then this Nullstellensatz system cannot refute this very, very simple statement efficiently in any way. Okay, so it seems a bit embarrassing, but sadly true. Okay. So, to some extent, proof complexity is about lower bounds, because we want to approach the NP versus coNP problem. But in some sense, getting lower bounds for very weak proof systems isn't really very interesting unless there's matching upper bounds to say these restricted proofs actually do interesting things. And so our first result is upper bound, saying that you can actually refute the subset sum axiom efficiently if you go to more succinct measures of algebraic computation. Okay, so the theorem here is that, again, you look at this system, sum of xi plus 1, and this has, it's false, and it has polynomial and n size IPS reputations. So in itself, this would be interesting because this would be general algebraic circuits. But actually, the algebraic circuits that you need here are actually a very restricted type, even of type. So I'll list 3 types. One is this baby case. It's not a technical term, but algebraic expressions of this form. If you can have proofs of this form of polynomial size that refute this system. But obviously, the baby case is not something previous that you can't Google this term and get this. But one of the things that you should note about this system here is that this is actually a multilinear formula. That every variable can only have degree 1. And whenever you multiply or when you do any intermediate computation, will also be multilinear. So this is actually a multilinear formula. So this system has small IPS reputations, which are multilinear formulas. And multilinear formulas are well known because Ron proved super-polynomial lower bounds for multilinear formulas, and it's a natural model for computing multilinear polynomials. The baby case is also interesting because they're not just multilinear formulas, but they have a certain variable disjoint property. Right? You can note that you have this summation of products, and each product is a product of variable disjoint things. And if you wave your hands enough, you can show that the baby case can also be expressed as a read once, oblivious algebraic branching program, which I haven't defined and I won't define. But this is a natural model of computation which captures things like the partial derivative matrix technique of Nissan and Ron. And has natural, I've worked a lot on this on polynomial identity testing and so on. So if you look at these models, these have short refutations for this proof system. So they even these restricted cases can do interesting things with proofs. But then there's a question, can you actually get lower bounds since there are interesting upper bounds there? And so the theorem here is that there are explicit sort of variants of the subset sum axiom. In the sense that you take this system, which is very simple, and you tweak it in a simple way, and you get some variant, which require various size bounds for these models of IPS proofs. So you can get exponential and n. So n will be the number of variables in the system. Exponential and n lower bounds for the baby case. you can get n to the omega log n lower bounds for multilinear formulas. And you can get exponential in n to the omega 1 for these read once ABPs. OK, so we're basically getting, I mean, n to log n is the best known lower bound for multilinear formulas as a computational model, so we don't really expect to get better proof lower bounds. But these others are basically matching what we know in terms of the upper bounds, right? Okay. And so I think Avishai, I think this is basically addressing your separation question, right? Because this requires large degree and sparsity, but has a small circuit. OK. So let me just briefly tell you what the variants are. So there will be two variants. One will be the inner product. So instead of just having one set of variables, you're going to have two. You'll have x and y. And we're going to replace a summation with an inner product. So here it's saying that the inner product is non-negative. And that will work for the baby case. And I'll give you an explicit proof of this lower bound. And then if you want to talk about these other two models, you need sort of a symmetrized model of the inner product. And so you can consider something like the following. You have, again, two sets of variables. You have x and z. And basically, the point is you're putting a zij here. You're summing over all I minus j. So you sort of have a complete graph amongst the x's. And you look at all edges, and you weight the ijth edge with the variable z. And the point here is that this polynomial, it's of constant is degree 3. Depends on all the variables, unfortunately. But it basically, under any partition of the x's, you can set the z's such that it embeds the inner product. Okay. And using that methodology and the existing lower bound techniques, you can lift this lower bound to get these. Okay. So in terms of lower bound techniques, we're not actually giving new techniques. We're sort of, to some extent, analyzing existing ideas and improving them in various ways.
Can you say again how is the inner product embedded in this?
So this is like a complete graph, right? You look at the xij's and you view them as a graph. The weight on the ijth edge is zij. So you have a graph something like this. And so suppose that someone came along and they said, you know what, I'm going to cut this graph in two, like this. What you can do is you can look at the edges. You can look at some matching that crosses this this partition, some perfect matching, say, that crosses the partition. And then you set the z's such that if the edge is not crossing, you set it to 0. And if it's crossing, you set it to 1. And then that, I mean, you don't get x's anymore. You get like y's and w's or something. That will embed this inner product. And by symmetrizing that appropriately, you get the whole point is that the inner product, to some extent, has maximal correlation in some way. And this allows you to embed maximal correlation across any cut of the variables. OK. So what I want to do before the break is just to tell you about two proof methodologies or ideas that we're using to get these lower bounds. So ideally what you would have is you could just read Ron's papers and just get these as corollaries. But you do have to do a little bit more work, and I want to tell you how that work goes. So there are basically two lower bound ideas, which I'll tell you about. So one is a so-called functional lower bound, and the other one is a lower bound for multiples. OK, so what's the first idea? So I'll call this a functional lower bound. OK, so a conventional lower bound is something like the following. You just want a polynomial f which requires large circuits to compute, right? So this is a computation a syntactic computation of polynomials, and you're saying any algebraic circuit computing this polynomial must be large. I want a sort of a stronger version of this conventional lower bound, which I'm going to call a functional lower bound. And so what is this? It's going to be some f hat, or hat, yes, f hat, which is a function from 0, 1 to the n to f, to your field f, such that whenever you have a polynomial f, so this is a function, and this is a polynomial. Whenever you have a polynomial that agrees with this function, that is f restricted to, right? Any polynomial, it defines a function on the entire field, but you can restrict it to the Boolean cube, and suppose that it agrees with f hat, right? Then I want to say that this implies that f requires large circuits. Okay. And that's what I'm going to call a functional lower bound. And this is some sort of hybrid between like a Boolean circuit lower bound and an algebraic circuit lower bound. Intuitively, you should expect these things to hold, because if you consider functions like the permanent is hard even for 0, 1 matrices. So if you had an algebraic circuit which agreed with the permanent on 0, 1, that'd be a bit surprising. It would like collapse the polynomial hierarchy, for example. So you could expect to get unconditional functional lower bounds, but it turns out that like you can't just go into previous papers and say, oh, functional lower bounds are there. It takes some work. And in particular, it's, even if you got such a functional lower bound, it wouldn't suffice for these proofs. You actually need to do something a little bit more. And let me tell you how that goes, and how we actually use these lower bounds to get IPS proofs. OK, so suppose you have a system of polynomial equations like this. OK, and notice that like the subset sum axioms are like this, that you have Boolean axioms and you have one sort of non-Boolean axiom. Okay, then what would a proof look like? A proof is something like g times f plus summation hi xi squared minus xi is 1. Okay, and from a perspective of proving lower bounds, this side is really annoying, because you have like multiple polynomials. Like we know how to prove lower bounds for a single polynomial. Like people have done this for ages. But now that you have multiple polynomials, you have the g's and the h's. And so we're going to do something stupid. We just want to sort of remove the h's and just like forget about them. And how does that work? Well, you just work modulo the ideal. Right? This expression, modulo the ideal, just says that g times f is equal to 1 modulo this ideal. Okay? And so now we just sort of forgot about the h's. And if we could prove that any g satisfying this equation must be of large complexity, that would certainly imply a lower bound on the g's and the h's, because we're really looking at the sum of the sizes of the g's and h's. So we only need a lower bound, say g in this case. Okay. And now the interesting thing is that this is an unsatisfiable equation, system of equations, because we're only trying to refute things that are unsatisfiable. And if this is unsatisfiable, it says that, it's unsatisfiable particularly because you have this equation. That means that g and f can never be 0 on the Boolean cube. Right? Basically, if working modulo this ideal is like working modulo Boolean vectors, saying so that you obey this functional equation that g times f is 1 whenever you have x 0, 1 to the n. Right? And so what you can do is you can then just divide by f, and then you get an equation of this form. Right? So if you have a proof, you get that g is 1 over f for every Boolean vector. So this will be our f hat. Right? We want to make sure that this f hat obeys that any polynomial agreeing with it on the Boolean cube must have large size. Okay, and if then it is indeed a functional lower bound, that gives us our IPS lower bound. God, you look confused. Hmm? Okay, so the main idea is that like, why do some people study algebraic complexity? It's because we really want to say that like you cannot compute the permanent with small Boolean circuits. I think that's what people really want to do. But they throw out their hands and we say we can't do this because it's really hard. So let's look at a restricted model. Computing the permanent as a polynomial is a restricted way of computing it as a function. So that's why people study algebraic circuits. Let's just study it as a polynomial and maybe we can get lower bounds there. Okay, that's still too hard, but you can still study restricted things. But I want to study some sort of mix in the sense that what I'm really interested in is not computing the permanent over the finite field of F7. I really want to compute the permanent over 0, 1. And I want to say that even computing the permanent over 0, 1 algebraically is still hard. And you would expect that to be true. And so this is saying that, look at, f hat is the permanent, say, on 0, 1 matrices. And we want to say that whenever you have a polynomial agreeing with this on the Boolean cube, it requires large circuits. So maybe let's do so I want to so like maybe an example would be just take f hat to be the permanent on n by n matrices. I want to say the functional lower bound for the permanent. So yeah, I mean the function is the lower bound. So I'm saying like I'm giving you a function like the permanent on 0, 1. I want to say for all polynomials, whenever they agree with the permanent on 0, 1 matrices, it must be large. And that's all I'm saying. That
okay, now this is your
right. So now I want to say, how does this apply to IPS lower bounds? So I'm going to say, suppose you had a system like the following. Let's just do a system of things and then relate it to functional lower bounds. If this is unsatisfiable, an IPS refutation must be of this form by definition. These HIs are very annoying. Let's just get rid of them. Let's work modulo this ideal. And then just say that implies that G times F is 1 modulo ideal. This is equivalent to saying that G is 1 over F for all Boolean vectors. And so if it was the case that this function, which we'll call f hat, has this functional lower bound property, that any polynomial agreeing with this function on the Boolean cube must be of large circuits, then that implies the IPS proof must be.
You need to choose F to be
Yeah, but you need to choose F carefully. Yeah, and the point is that you need to choose F such that 1 over F is a functional lower bound, which is a bit strange, but.
Don't you have such Fs, like the permanent, take 1
So that's the weird thing. It's like,
the permanent is not a polynomial.
yeah, 1 over the permanent's not a polynomial, and then
A polynomial is one.
right. And in particular, the thing that's weird is that so what do we need? So the thing about proof complexity is that you want the statement of the proof to be simple. So if the statement was the permanent of this matrix is 0, that's not really a simple statement because you can't compute the permanent efficiently. So what we really need is that we need that f itself is simple. And ideally it'll be constant locality. Well, it's not going to be constant. Ideally, it'll be constant degree. So ideally, you have a constant degree polynomial as f. That's something that you need. And that's because you want to encode the statement of the axioms to be in a small way. And then you want that 1 over f is hard in some sense. In particular, you want it to be this function to be a functional lower bound. Right, 1 over f itself, I mean, we're not looking at this as a polynomial or a rational function. It's just 1 over f modulo the Boolean cube. That's a hard function somehow. So it's sort of strange. It's like f is simple, but 1 over f is hard. And that's exactly what's going on here. That like these polynomials are very simple. Like they have linear size circuits in basically every model that you can think of. And yet somehow 1 over this polynomial is a hard function. For algebraic circuits, at least. I mean, for Boolean circuits, it's like taking 1 over something is fine. Like that's not really a big deal. But the point is that with algebraic circuits, you don't really, I mean, you can have division, but there's an issue. I mean, yeah. Yeah, because once you have 1 over something, it's not even a polynomial anymore. OK. Yeah. And yeah, I guess we should just take a break then. I want to tell you now about something I'll call lower bound for multiples. Okay, and this is not as useful in this result. I'm not going to give you any lower bounds for multiples, but let me just tell you what it is since I think it's really cool. Right, so the conventional lower bound is just a polynomial which requires large circuits. Okay, well now I want a polynomial f such that all non-zero multiples require large circuits. Okay, so what does that mean? It means that like, f squared, f times x, all of these things require large circuits. Okay, and so this is like, you would kind of expect this to be true to some extent, because if you consider the determinant, it's very non-sparse. It seems like if you multiply the determinant by something, it should still not be sparse. That's in some intuitive statement, but there's some challenges in proving something like this, right? Because if you consider something like 1 plus x squared plus up to x to the n, right? This has n plus 1 terms, right? But then if you multiply it by, x minus 1, you get x to the n plus 1 minus 1. So the sparsity has gone down.
Cancellation.
Right, so you have some magical cancellation, right? And so it's not, it seems like, you can't just take any polynomial which is hard and say that all of the multiples are hard to some extent. And it requires some work, but it turns out that in some cases, you can lift existing lower bound techniques to get lower bounds for multiples. And actually, there's interesting reasons for doing this because it has some natural connections with hardness versus randomness. But let me just tell you right now.
Why do we need lower bound for multiples?
So I'm going to tell you how to get IPS proofs lower bounds from that. OK, so again, what we're going to do is consider equations of this form. So again, you have Boolean axioms, and then you have one non-Boolean axiom. And let's just consider this statement, right? This equation again. We're going to move certain parts to the other side, and we're going to get that g times f is 1 minus summation hi xi squared minus xi. Right? Again, these hi's are sort of pesky. I don't know how to deal with multiple polynomials. I only know how to deal with one. The point is that suppose this IPS proof was small, like very simple. Right? Then the right-hand side should in general have a small algebraic circuit because the hi's do. These are very simple polynomials. So this whole thing should have a small circuit. Right? And so what this is saying is that there is some multiple of f that has a small circuit. So if it was the case that all multiples of f required large circuits, then there can be no small IPS proof. Okay. Yeah. Okay. So that's where I'm going to leave it. But there's this natural question, which Ron asked me during the break. All of this machinery is sort of built when there's Boolean axioms and one non-Boolean axiom. And in particular, you cannot encode CNF formulas this way, because if you take a CNF formula and you encode it as a polynomial system of equations, you're going to get one equation for every clause. Right? And so you're going to get many, many polynomials. And these ideas don't seem to work. Right? So the main open question of this work is lower bounds for equations encoding CNFs. Or even just multiple polynomials. Like one thing that you can consider is if you look at this equation, this is one hard equation and Boolean axioms. But you can encode this differently. Right? You could say, for example, instead of this system, you had something like summation zi, and then you have equations like zi minus xi, yi is 0. And then you put the Boolean axioms here. Right? You could consider this system. Right? This is basically the same system of equations because these equations enforce that you're basically computing an inner product. So before I did this modification, it was hard. But actually, after the modification, it becomes easy. And the reason it becomes easy is now you have the subset sum axiom. You can basically forget about the x's and y's. You can just look at the z's. And you can refute that the subset sum is satisfiable. And you can refute that using, say, multilinear formulas.
But you have an external limit there.
Sorry?
You have the zi minus x. What do you do with this?
You basically don't need to forget. You can forget about it because no matter what basically the way to think about it is, I just need to prove that this system is unsatisfiable. And if you
say that it's unsatisfiable even if you forget about it?
Yeah, even if you forget about the z's and x's and y's, it's still unsatisfiable. So you can refute this without ever touching the x's or y's. And so somehow, like, these lower bounds are very encoding sensitive. That, like, when you do the natural, like, you can reduce things like general set to 3C and F, right? And that shouldn't change the complexity of the proofs, but in this situation, it's like very brittle. But again, there were no lower bounds before, so you do what you can do. OK, so now what I want to do is I want to prove some stuff for you instead of just talking. What do I want to do? Right, and I want to prove the lower bounds first, and then I want to tell you about the upper bounds if we have time. Unless someone wants something else. But OK. So what's the lemma I want to prove for you first is I want to prove actually a degree bound. So I said degree is sort of a silly measure, but actually I care about it a lot still. And I want to get a degree lower bound first. So suppose that you have g of x. So I'm going to go around. I'm going to prove this baby case lower bound using this functional lower bound idea. So suppose that g of x is this is a polynomial here, and this is a function. So this is a functional equation for every Boolean vector. I want to say that this implies that the degree of g is at least n.
So now we're looking at the subset sum?
Yeah, so I'm going to look at the subset sum one, and then I'm going to lift it to the inner product. OK. So I want to say that you look at the subset sum, and I want to get a functional lower bound for subset sum in terms of degree. OK. And if you look at this lemma, and you're like an expert in Boolean function analysis, you can say, oh, well, we know that this is a function. It should have a unique multilinear representation. You just compute that, and then you observe that it's degree n. OK, you can do that. I'm just going to do another proof for you if you're not an expert in Boolean function analysis, because I'm not myself. OK, so let me just make a couple of remarks, though, about this. First of all, of course, there exists a g where the degree of g is equal to n, right? So this is a tight bound. Just make that remark. This in Pagliazzo, Pudlock, Segal, right? They studied this subset sum thing, and they proved a degree lower bound of n over 2 in a slightly stronger model, which I'm not really going to discuss. But I want to emphasize that degree n over 2 is not going to be enough for me to lift it to the inner product. So you really need like a tight bound here, and we'll see why that is. Yeah, so we need the degree is n. OK. Right, so we can first make some simplifying assumptions without loss of generality. First of all, g is a polynomial. We can assume it's multilinear, right, because there's a unique multilinear polynomial agreeing with this function. And multilinearity, if you take a polynomial and reduce to its multilinearization, it only decreases the degree, so it only makes it better. We can also assume that it's symmetric, because in all of the variables, like this is a function, and it's symmetric in its function in its variables, so you can assume that this polynomial is multilinear and also symmetric. OK. And as a consequence, right, that means that we can express, say, g as a linear combination of elementary symmetric polynomials. So you can consider, g will be a combination of this, and this is the elementary symmetric polynomial of degree k. OK, and so d will be the degree of g here. OK, and the basic lemma that we want to understand is that this is a functional equation, which basically says that if you take the subset sum axiom and you multiply by g, you get 1 modulo the Boolean cube. And we want to understand, well, if you take the subset sum axiom and you multiply by a symmetric polynomial, what does that do?
Can you remind us the geometric polynomial?
Yeah. So this is, you sum over all take n and choose k, so every k subset of n variables, and then you product over everything in that set. Yeah. OK. So the lemma here is that if you take this subset and axiom and you multiply by sk, we want to understand what is the unique multilinear polynomial agreeing with this. Right? This is not multilinear because this depends on each variable and this depends on each variable. And if you work it out, which I'm not going to do for you, you basically get the following. That the unique multilinear polynomial agreeing with this polynomial is a linear combination of the k plus first elementary symmetric and sk itself. And there's some coefficients and so on. And the point is that sk is degree k, and sk plus 1 is degree k plus 1. Right? And I mean, intuitively, if you didn't have the multilinearization, multiplying a degree k polynomial and degree k plus 1 polynomial should give you degree k and degree 1 should give you degree k plus 1. But after you multilinearize, you may decrease the degree. What this lemma is saying is that even in this specific case, multiplying actually still increases the degree from k to k plus 1. All right, so what's the corollary of that? Is that suppose that the degree is at most n. Right, so the point in this lemma, this is assuming that k is strictly smaller than n because there is no n plus first elementary symmetric polynomial. So because of this degree increasing lemma, d was degree d strictly less than n, then what it's saying is if you multiply the subset sum times g, well, this is equivalent to some g prime modulo the Boolean cube, and the degree of g prime is d plus 1. Right, so it's saying if the degree is too small, you multiply by a subset sum, and you get degree which is 1 bigger. Just complete it over here. Right? But the point is that if you look at this functional equation, right, you have that g is 1 over summation xi plus 1, which is equivalent to saying the summation xi plus 1 times g is equivalent to 1 modulo the Boolean cube. Right? And this is 0. Right? And so 0 is never d plus 1. So it must be that there must be a wraparound effect to combat the fact that this is always degree increasing. Okay. Okay, so that's a proof that you necessarily get like maximal degree, which you can also prove by doing the unique multilinear expansion if you want, but that's more technical. Okay, so let me just derive for you now. Okay, so I mentioned that IPS 99, it's erased now. Right, they got a degree lower bound of n over 2, and that gives you the IPS this degree lower bound. But what about the sparsity bound? So let me just rederive briefly how do you get the sparsity lower bound. Right, so I'm going to state this as a functional lower bound. So suppose that you have that g is 1 over the subsystem axiom for all Boolean vectors. I want to say that implies, this is again a polynomial, that the g of x requires exponential in n many monomials. So g is very non-sparse. I don't want to get that directly from the degree bound.
Now can you assume
Yes, because multilinearization only decreases sparsity, I think.
So what are we doing? So we know that g is maximal degree.
Right, so we know that g is maximal degree, but it could be that g is, it could just be that g is still very sparse. That's conceivable. But we want to say that we can rule that out, actually. So I'm not going to give you the full proof. I'm just going to sketch it. And the key idea here, well, there are two ways to do it. But one way to do it is basically with random restrictions. Basically, you set xi to 0 with probability p, and you choose p carefully. And what does that do? Well, you have your subset sum axiom. Right, so this is a functional equation which you can view as something modulo the ideal. And that equation will still hold even if you set variables to 0, because you're setting them to 0, and that's OK within the Boolean cube. If you do your random restriction and you call it rho, well, this will be something. Now you get a subset of the variables. Right, so the point is that random restrictions to the subset sum axiom preserve the structure of the subset sum axiom. And a key thing about random restrictions is that if you have a sparse polynomial, it turns out that sparse polynomials under random restrictions become low degree. And the intuition for this is that if you choose p carefully, if you consider a very high degree term like x1, x2, xn, this is a very high degree term. But the point is that if you set variables to 0, then with high probability, this will just get annihilated. Right? And so you set p carefully such that you can do a union bound. And the reason you're using sparsity is because you use the sparsity to argue that you don't union bound over too many things. Okay? So the way this proof goes is you do this from random restriction. You go from sparse to low degree. You basically have the same problem, and then you invoke the degree bound. Right? OK.
Another way is just like as you said, there is only one way, like a unique way to get G.
Right, G.
You can just analyze. Right?
Yep. Yeah, that's true. I didn't think about that. Yeah, I mean, I did the formula for G, and it's everything's on 0, I think. So it's actually like maximally sparse. Yeah, we wrote it. Yeah, it's in the paper. But I mean, G is symmetric, and you can explicitly compute the coefficients of the symmetric polynomials, and they're all non-zero. Okay. Right. Okay. Okay, so now what I want to do for you is I wanted to move towards this lower bound for the baby case. And let me just, since I erased it conveniently, let me remind you what this is. So you're going to have do something slightly different. I'm now going to, because I eventually want to move to the inner product, I want to have two sets of variables, x and y. I want to distinguish them. And what does one of these baby case computations look like? Just to remind you, you have a summation, j from 1 to r. You product I1 to n. Here you're going to have some alpha ij xi plus beta ij. So this is some linear thing only in the variable xi. And then because I distinguish x and j, x and y, you have now another thing for, let's call this gamma, I guess, yi plus. You have a similar term for y. Okay, so this is a sum of products of linear univariates. Okay, and so now I want to, tell you about some methodology for getting lower bounds for this model of computation. Okay, and the measure I'm going to give you is basically this partial derivative matrix of Noam and Ron, but I can call it something slightly different. I'm going to call it something called evaluation dimension, which is the following. So suppose you have an arbitrary f of this form, not necessarily written like this. I'm going to say that the dimension of evaluations, or partial evaluations, with respect to a set S of f is the following. So I'm going to view x and y differently. I'm going to partition them. And I'm basically going to take every value. I'm going to take every input in x, and I'm going to evaluate them with arbitrary elements from S. And I'm going to look at all of those partial evaluations. OK, so I'm going to consider x is going to be untouched. I'm going to replace alphas. So S will be a subset of your field. And you can think of this as just 0, 1, because that's what it's going to be in the end. So you're going to take f. X is going to be untouched. You're going to replace y with some alpha. And what alpha are you going to choose? You're just going to choose all alpha where alpha I is in S. OK. And so you could all variables in, so yeah, so this will be like y1, or this will be alpha 1 up to alpha n. And for all I, alpha I will be in S. OK. So this is some set of polynomials associated with the function, the polynomial f. And this may be a very, very large set, like exponentially large, for example. And so counting the number of polynomials in this set is not particularly useful. We need like a more refined measure of counting. And one measure is to view the set of polynomials in the vector, as a vector space and look at its dimension. OK, so this is a set, and it's contained in the ring of polynomials in X. And this is a finite dimensional vector space, or not a finite, but these are bounded degree. So this is basically lies in a finite dimensional vector space. And so what we want to do is measure the dimension of this set. This will be our complexity measure. OK, so the whole point is that we want to say that when we have f to be simple, say simple arising from this baby case computation, we want this dimension to be small. And then our target polynomial should have large dimension. Right? And so what's the proposition? Do something illegal and just say, take this formula and you copy it over here, since I don't want to write it again. I want to say that in this case, the dimension of the evaluations is actually at most r. So what is r? R is the size of this summation. This is the only size measure of this entire computation. Like this, there's one product for every variable here, so that's never going to change. It's just r, right? And this is a complete model of computation, so you can compute any polynomial as long as r is exponential. But the efficient version of this is when r is small, right? And we want to say that for these computations, the dimension is just at most r. OK. So what is the proof? Yeah, this will be true for any set S that you choose, actually.
So this only give you the y only give you like a coefficient which is constant in the field. So
yeah.
So you are spent by the.
OK. Yes. So. Is that OK? OK. Maybe I won't write it. But basically, yeah. I mean, I'm a bit pedantic sometimes. Basically, when you substitute the y's, right? What I was saying is that this entire product becomes a constant, right? And so then you basically are spanned by, because you can basically focus on one thing. Basically, it's now a linear combination of these products, and there are of them, and so that dimension is r. Okay. This is It's so simple. That's why I restricted to this baby case. OK, but good. And now we want to do the lower bound, which is more interesting. OK, so what is the theorem? The theorem is that suppose you have G. It's going to be an x and y, and it obeys this functional equation where you have this inner product. Where x and y are Boolean. Then I want to say this implies that the dimension of these evaluations of G are at least exponential in n, 2 to the n. But I need to choose my set carefully. So I had this definition where I'm evaluating the y's from some set S. And the reason I put this notation here is because I'm not going to prove this for an arbitrary set. I'm going to prove it for the set 0, 1. And I want to just dwell on this point for a sec, because this is where I just erased it. OK, great. But this is why we're using a functional lower bound, in the sense that all I know about G is its functional behavior on 0, 1. Right? So I don't know about its evaluation dimension when S is like 2, 3, or 5, 6. Right? I only know about its behavior on 0, 1. And so this is actually somewhat unique in algebraic complexity, that this measure, to some extent, only depends on the functional behavior of f to some extent. Whereas like there are other measures, like based on partial derivatives, which are actually highly non-local. That based on, like, if I tell you a polynomial and I only tell you its behavior on 0, 1, it does not tell you anything about its partial derivatives. So there's some techniques which work with functional lower bounds and others that don't. This evaluation dimension is functional, so it works to some extent. OK, so let me just give the proof here. OK, so well, OK, let me give you the corollary first. Like, why are we proving this, right? This just says that, right, that any IPS refutation of this inner product function, at least in this baby case, it requires exponential size. Right, and this is basically just piecing together what I just erased, basically saying that, for computation in this baby case, the dimension is small, this function is hard, and then you apply this functional lower bound idea. OK. Yeah, but OK, the proof is basically looking at this space of evaluations and arguing that it is large dimensional. And we're going to leverage this degree bound, which is why I proved it for you. OK, so first of all, what is this evaluation space? So if we evaluate y, right, all I'm telling you is some functional behavior of G. So if I evaluate G with some setting of y, I'm going to get some polynomial. I'm going to call this G sub t, and I'm going to identify t with subsets of n. And I can do that because I'm evaluating y over 0, 1, so I can identify the Boolean cube with subsets. OK, so I take G, which is a polynomial. I get a space of polynomials, right? And as of right now, I mean, I can't say anything necessarily about the polynomials, but what I can say is I can say something about their functional behavior, right? Because I can inherit this functional behavior from G itself. So G of t obeys the functional equation, which is a subset sum axiom. But it's not exactly a subset sum axiom. It's a subset sum restricted to the set T. Right? Basically, what you're doing is you're setting some of these y's to 0 and some to 1. And the ones that are 1 define the set T. And then you basically get a subset sum in that set T. OK, so now we have this space of polynomials, and we have some understanding of individually their functional equations. And now I want to argue that this space of functions is related to the space of polynomials in terms of dimension, and that we have linear independence. OK, so the claim here, this is a bit of a subtle point, is that right, the space of partial evaluations of G, which I'm just dropping some notation, this is a space of polynomials, because you just do a partial evaluation. But I want to relate this to a space of functions, and I want to say this is at least the dimension of the space of functions given by these subset sum axioms. OK, so here, this is a space of functions. A space of functions from 0, 1 to the n to the field. And I want to say the dimension of the polynomials is at least the dimension of the space of functions. Right? Functions here, this is still it's a linear space. Okay. And the way to see this is basically that you're basically, I mean, the evaluation map from a polynomial to a function is just a linear space because it's an evaluation map. So this is something you have to sort of do in the privacy of your own home, but it's true. Okay, and now we want to say, so this is what we wanted to bound, and we're lower bounding it by the space of these functions. And now we want to say that these functions, int, these are linearly independent. Okay, and that would prove the claim because this is a space of functions. They're parameters by subsets. There are 2 to the n subsets, and that's the dimension bound I wanted. Okay, and so why are they linearly independent? Well, as sort of been mentioned, right, there's a unique multilinear representation for functions. Right, this is a function, but I can think of it as a unique multilinear polynomial. Right, so convert to its unique multilinear polynomial, which is in fact a invertible linear map, so I haven't really changed the dimension at all. And I want to say, now I want to show that these polynomials are in fact linearly independent. Okay. Now, what do we know about these polynomials? Well, they're just subset sum axioms, right? And so what do we know? Well, first of all, it's pretty clear the degree is at most the size of the set, right? Because this is a function which basically only depends on the variables in the set. So the degree is at most that. But at the same time, the degree is at least the size of the set, because as a subset sum axiom, and we prove this lower bound, right? And so from this, we can conclude the degree is actually equal to the size of the set. And what does that mean? Well, it's a multilinear polynomial which has degree equal to the number of variables. And so that says that the leading monomial, like the largest monomial that has a non-zero coefficient, is just the full monomial of xi when you product in t. Right? Okay, so it's saying that this function, when you look at it as a multilinear polynomial, the leading monomial is this. And note that this monomial depends on t, and this leading monomial is unique given t. Right? So that's saying that the leading monomials are all distinct. Okay? And if you sort of write it down as a matrix, what you basically get is that this is a triangular system of vectors. Like if you take these polynomials, you write them in a vector representation in the appropriate way, you get a triangular matrix. So they're linearly independent. Okay, and so that completes this. Okay, so what this is saying is that we define this complexity measure, which is based on these partial evaluations, and we did that because we can extract information about this from functional representations, like the ones given from IPS. This baby case is very simple to analyze and clearly has a small measure in this evaluation dimension. We can then look at this inner product function, look at its space of evaluations, convert those to functions, and then using this leading monomial argument, we reduce to the degree bound. That gives us linear independence, which is pretty simple. And I mentioned before that when I was doing this degree bound, that we really needed the degrees equal to n here, and you can kind of see why. Like if I told you that the degree is at most t, but it's at least t over 2, I couldn't really conclude that this monomial has a non-zero coefficient, and I wouldn't really get this leading argument, the leading monomial argument. Maybe you could make it work, but it seems a bit harder to do so. So it really we really needed a tight result in all situations. Okay. Yeah. So this thing. Yeah, let me rederive it since I erased it. So basically, right, we want to consider an IPS refutation of this system, and what would that look like? Right, you have g of xy, you multiply it by this inner product thing, and then you have summation, hi xi plus 1 plus summation hi prime. All right, so an IPS refutation would be something like the following. And then we say, well, these things are very inconvenient, so let's just work modulo the Boolean cube, in which case we get that this is true modulo the ideal. And then we say, well, this ideal equation is basically, you can work modulo the Boolean cube as evaluations, and you can get that this is equal to this thing as a function whenever you have that x and y are Boolean. So any IPS refutation necessarily gives you a polynomial that equals 1 over the inner product for all Boolean vectors. And we're assuming that, G here, this is computable in, say, size R in the baby case, which implies that the dimension, the valuation of G is at most R. And this, this is at least 2 to the n.
So this is what that is.
Yeah.
So it's computable in the dimensions.
OK, yeah. All right, thanks. Yeah, OK. OK, so now let me just state like the more interesting corollaries. Like this baby case, it's an interesting test case for algebraic computation, but it doesn't, it's not as powerful as other things. And so what's like the more powerful version of these results, which I sort of already stated, but I'll say it again. So you consider this axiom. You have xi and xj. This plus 1 is on the outside. You weight it with zij, and you sum over all I minus j, I less than j, and you throw in the Boolean axioms. And then basically, and you say that this requires, it's a false statement. It's unsatisfiable. And it requires IPS refutations, say of size n to log n, with multilinear formulas. It didn't really define, but basically are formulas where every intermediate polynomial is multilinear. OK, so if you have IPS proofs where all of the circuits have multilinear formulas, you must have this size. And basically, how do we derive that? Well, basically, the sketch is that what Ron was able to prove is that when you have multilinear formulas, if you do sort of a random partition, so you think of the z's as sort of indicator variables or control variables. So they're not like real in some sense. But what Ron was able to show is that if you look at the x's alone, then if you pick a random partition, the multilinear formula will have slightly less than maximal evaluation dimension. OK, so a random partition of the x's has sort of non-maximal dimension of the evaluations. OK. And then what you do is this is what Ron was able to show, and then you just choose your z's carefully. So what I mean by that is that you take your x's, you randomly partition them into 2. The multilinear formulas will have slightly less than maximal evaluation dimension. And then you choose your z's such that you embed the inner product exactly in that partition. And the inner product has maximal evaluation dimension. And then you sort of just compare, and you get the lower bound. OK. And then the one for read once AVPs goes the same way. So that's not super difficult. OK. So I have about 10 minutes. I just want to sketch to you some ideas that go into the upper bound, unless there are any questions about the lower bound.
What was the third model that you had outlined on?
So there's read once algebraic branching programs. I can define that if you want. But
No.
OK. Yeah, but the model also would go, the proof would also use this evaluation dimension. But it's a bit even simpler, actually. OK. So now I just want to briefly sketch some ideas that go into the upper bounds, saying that, I told you about lower bounds saying that, the inner product thing cannot be done. But what about just the subset sum axiom? I want to get the separation result from sparsity. Right, so what's the theorem here? Right, is that you have xi plus 1, summation xi plus 1, and the Boolean axioms, and this has a poly-n-size IPS refutation. So I won't be able to sketch to you the full proof of this even, and I won't even be able to sketch to you like why you can actually put this in restricted models of IPS, but I'll just give you some of the ideas. Okay, so let's just remind you what we want. Right, we want a g of x such that we have the following. Right, we want g and h such that this equation holds. And sort of as the recurring theme here is that it's really annoying to consider the h's. So what I'm going to do is I'm just going to forget about them. And what we want to do first is we want a g such that if you go modulo the ideal, you get the required equation. All right, we first just want a g such that this is true. And we want g to have a small circuit. OK. And if we can do that, then that's at least a first step to show you that this is like plausible. OK. OK, so what's a preliminary lemma? Let's consider the following. Suppose that you have a p of t, which is a univariate. So it's a univariate polynomial. It's nothing too complicated. Then if you consider x minus y, it divides p of x minus p of y. OK, it's not a very difficult lemma. It's basically saying that you can divide and you get a polynomial. OK. So what does this imply? Is that p of x minus p of y divided by x minus y. First of all, it's a polynomial, right? That's pretty simple. But second is that this is a bivariate polynomial. There are only two variables, x and y. And so this has a polynomial in the degree of p size circuit. So p has some degree, whatever that is. And you can compute this polynomial in that degree, okay? Because it's a bivariate, there's only two variables. OK. And now we want to use this to refute this subset sum axiom. So what p are we going to choose? We're going to choose p of t to be t minus 0 times t minus 1, t minus 2, up to t minus n. OK, and why are we choosing this thing? It's because 0, 1, 2, 3, 4, up to n, those are the possible values of summation xi plus 1. Or I guess 0 is not needed. OK, I'll just leave it in, whatever. OK, so these are the possible values of the subset sum axiom. And this is degree, OK, I'll just remove this, degree n. Well, I guess you get n plus 1. OK, so it's a degree n plus 1 polynomial. Which encode the values of the output of this subset sum axiom. Right, so what does that imply? It says that p of summation xi is congruent to 0 modulo the Boolean cube. Because no matter what Boolean vector you put in, you always get 0. Right? OK, so now consider summation, p of summation xi minus p of minus 1 divided by summation xi minus minus 1. Right, so I'm using this lemma and saying this is a polynomial. Right? So this is a polynomial, and it has a small circuit. And now multiply this by 1 over minus p minus 1. And I'm going to call this g. I'm going to say this is my g. OK? And let me just now, so what are the claims? So first of all, that g is a small circuit. And why is that? It's pretty simple. I mean, p itself has, like this quotient has a small circuit before you did the substitution, because it's, it's a bivariate thing. And now you're just, this thing here, this is a constant. It's a non-zero constant. And so I just plugged in the summation, and so that preserves everything having a small circuit. Right? Right, so that's one claim. And then the second claim is that we just need this thing to obey the functional equation. Right? We need this to hold. And let's just see what happens. Well, if you multiply the subsystem axiom by this, well, that's exactly the denominator. Right? So then you just get p of the summation minus p of minus 1 divided by this constant. But this thing is 0 modulo the Boolean cube. So then you just get this constant divided by itself, and you get 1. Right? OK. So that basically shows that at least you have a g, which is a small circuit and obeys this thing. So, what about the HIs? Well, it's before lunch, and I'm not going to do it, basically. But you need to show some sort of efficient multilinearization. So what I mean by that is basically that this is something. This is, if you take this polynomial minus 1, it's 0 modulo the Boolean cube. That's the statement of the equation, right? And I need to basically prove to you that it is 0 modulo the Boolean cube. And what that means is basically I have an algebraic circuit, which is 0 over the Boolean cube, and I need to prove it to you. Now, in general, this is not an easy thing. This is like multilinearization is not necessarily is not efficient in general, at least as far as we know and we suspect. But it turns out that for these specific types of reasoning that we've done, you actually can multilinearize efficiently. So that's a very vague statement, which is not supposed to make sense, but it's true. Okay, and then in these, so that's one thing you need to do to make this a genuine IPS proof. And then I wanted to actually get this into the restricted models of computation, things like the baby case, and this is just more work, which I'm not going to tell you about, but is there. That basically, this is not an arbitrary computation. You can sort of do tricks and so on to get it into the baby case, and that gives you this nice upper bound, which gives you this separation.
Can you please repeat what you said about the H's?
OK, so to get an IPS refutation, you need an equation of this form.
Yes.
Now, for the lower bounds, all we were showing was that g must be large. What we've done now is we've just shown that g is small. But this is not really enough. You also need to show that the h's are small. So basically, if you look at this polynomial, this thing minus 1 is 0 modulo the Boolean cube. And so you need to be able to express this somehow with efficient h's. And for arbitrary g, it's not really possible. Or like it's probably like if you assume like the polynomial hierarchy collapses, it doesn't have collapse or something, it shouldn't be possible. But basically, if you analyze this expression enough, you can actually do it. You can basically like this is not a multilinear polynomial, but you do some process where you multilinearize variables one by one. Like you have an xi squared, you replace it with an xi. You sort of do this one by one, and you can show that amongst this process, it remains all the circuits remain small. But it's not something that works in general. But it's still vague. I'm not sure that makes sense.
Because I understand what needs to be done.
OK. OK, well, that's it, I guess.